After introducing mathematical induction, we introduce a very similar but slightly more confusing proof technique, which is called strong induction. Again, consider statements Pn for each positive integer n. If we can show that P1 is true, and given that P1, P2 up to Pk are true, Pk plus 1 is also true, then Pn is true for all positive integers n. The difference of this from mathematical induction is that in the inductive case, instead of assuming that just Pk is true, we assume that all statements from P1 up to Pk are all true in order to deduce that Pk plus 1 is true. At first sight, it seems that the strong induction made a stronger assumption compared to mathematical induction, but in fact they are equivalent. Let's see how mathematical induction implies strong induction. For this, we assume that conditions S1 and S2 hold, and we have to show that Pn is true for all positive integers n. Now, we define Qn as P1 and P2 and all the way to Pn. In order to apply mathematical induction on Qn, we need to show that conditions M1 and M2 hold for Qn. First observe that the condition M1 holds if and only if Q1 is true, which is equivalent to P1 is true, which is equivalent to the condition S1. Since we have assumed that condition S1 holds, we know that condition M1 holds. Then, for condition M2, suppose that Qk is true. Since Qk is P1 and P2 and all the way to Pk, Qk is true implies that P1, P2 up to Pk are all true. Then, using condition S2, we have that Pk plus 1 is true. So now, P1, P2 up to Pk and Pk plus 1 are all true, that is, Qk plus 1 is true. This means that condition M2 holds. By mathematical induction, Qn is true for all positive integers n, which means that Pn is true for all positive integers n. As an example, let's prove that every positive integer n, where n is greater than 1, is a product of prime numbers. Here, we cannot use mathematical induction because the knowledge of the prime factorization of n has no direct relation to the prime factorization of n plus 1. However, we can prove the statement using strong induction. The base case is 2, which is itself a prime. So 2 is a product of 1 prime. So the base case is true. Assume inductively that 2, 3, 4 up to k are each a product of prime numbers. Now consider k plus 1. If k plus 1 is prime, then k plus 1 is a product of 1 prime. If k plus 1 is not prime, then there exist positive integers a and b such that a and b lies strictly between 1 and k plus 1, and k plus 1 is a times b. Since 2 is less than or equal to a and b, and less than or equal to k, we can apply the inductive hypothesis to both a and b to get that a and b are each a product of prime numbers. Since k plus 1 is a times b, k plus 1 is also a product of prime numbers. This completes the inductive case, and so the result follows from strong induction. Let's look at one more example. The Fibonacci sequence is defined inductively as follows: f0 equals 0, f1 equals 1, and fn equals fn minus 1 plus fn minus 2 for all positive integers at least 2. We want to prove that fn has the explicit form 1 over square root of 5 times bracket 1 plus square root of 5 over 2 raised to the nth power minus bracket 1 minus square root of 5 over 2 raised to the nth power. We first check that the base case is true. When n equals 0, 1 over square root of 5 times bracket 1 plus square root of 5 over 2 raised to the 0th power minus bracket 1 minus square root of 5 over 2 raised to the 0th power equals 1 over square root of 5 times 1 minus 1, which equals 0, which equals f0. Also, 1 over square root of 5 times bracket 1 plus square root of 5 over 2 to the first power minus bracket 1 minus square root of 5 over 2 to the first power equals 1 over square root of 5 times square root of 5, which equals 1, which equals f1. So the base case is true. Now assume inductively that fk equals 1 over square root of 5 times bracket 1 plus square root of 5 over 2 raised to the kth power minus bracket 1 minus square root of 5 over 2 raised to the kth power, for k equals 0, 1, 2, all the way up to n minus 1. So we compute fn minus 1 plus fn minus 2 as 1 over square root of 5 times bracket 1 plus square root of 5 over 2 raised to the n minus 1th power minus bracket 1 minus square root of 5 over 2 raised to the n minus 1th power plus 1 over square root of 5 times bracket 1 plus square root of 5 over 2 raised to the power n minus 2 minus bracket 1 minus square root of 5 over 2 raised to the power n minus 2. We can take out the common factor bracket 1 plus square root of 5 over 2 raised to the power n minus 2 from the first and third terms to get bracket 1 plus square root of 5 over 2 raised to the power n minus 2 times 1 plus square root of 5 over 2 plus 1. Similarly, we could take out the common factor bracket 1 minus square root of 5 over 2 raised to the power n minus 2 from the second and last term to get bracket 1 minus square root of 5 over 2 raised to the power n minus 2 times 1 minus square root of 5 over 2 plus 1. Next, we write 1 plus square root of 5 over 2 plus 1 as 3 plus square root of 5 over 2 and 1 minus square root of 5 over 2 plus 1 as 3 minus square root of 5 over 2. Now, observe that 3 plus or minus square root of 5 over 2 is the square of 1 plus or minus square root of 5 over 2. So, at last, we have 1 over square root of 5 times bracket 1 plus square root of 5 over 2 raised to the nth power minus bracket 1 minus square root of 5 over 2 raised to the nth power, and this completes the proof.